Hi everybody, this is Mrs. Alcorn and I'm here to teach you about the greenhouse effect. You will be able to identify the gases in the atmosphere after this video. You will be able to list the greenhouse gases and their sources. So Earth is somewhat comparable to a greenhouse. The gases in the atmosphere acts like the glass and they trap heat and energy from the sun. So as that light comes in, some of it gets reflected back into space, and some of it gets trapped by the greenhouse gases and the bonds of the greenhouse gases and stays there, and that energy is converted into heat, and the atmosphere holds this. Without any greenhouse gases, we wouldn't be here. We need it to keep the planet a habitable place for beings such as us. However, the problem is that there's more greenhouse gases than the Earth needs right now, and it's causing a lot of problems. Oh, let me move my face. Check out this video that demonstrates this.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18°C, and even deadlier, they range from -170°C during lunar night to 100°C at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the Moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
Okay. So how does the atmosphere trap heat? So first, let's look at what gases make up our atmosphere. 78% is nitrogen, N2 gas. 21% is oxygen, O2, and that's what we need to breathe and stay alive and conduct cellular respiration. A pirate's favorite gas, argon, is about 1% of the atmosphere, and then other gases, 0.1%, comprise the rest. And you might think, oh, 0.1%, that's insignificant, but it's really not if you think about how vast and massive our atmosphere is. So greenhouse gases specifically are gases that absorb and radiate infrared radiation. And the most common ones are water vapor, carbon dioxide, methane, and nitrous oxide. So others include ozone and CFCs, which are chlorofluorocarbons, which my HVAC kids will know all about. Now, not all gases are greenhouse gases. Not all of them have a bond structure that allows them to absorb energy and to re-radiate it as heat. It's infrared radiation. And that can be confusing to people. So nitrogen gas, for instance, N2 gas is not a greenhouse gas, whereas nitrous oxide is. So water vapor has this ability, H2O, the way that the bond structure of water is set up allows it to re-radiate heat, absorb and re-radiate the heat. So this is not considered to be an anthropogenic derived greenhouse gas from, it's not released into the atmosphere through human sources, but directly. It is indirectly though. So we all know, hopefully this is a review, that water evaporates and gets into the atmosphere. When it evaporates, it's going from a liquid to a gas to water vapor. Then you can have precipitation. I used to know a song about this and can't think of it. So sublimation, a new term, maybe a new term for you. That's when you go straight from a solid to a gas. That's when there's really intense energy on a solid, like on snow, if it's really bright, on snow or ice up the mountains where there's the concentration of oxygen and other gases is lower. The sun can be really, really bright and direct, and it can actually take those the snow and the ice and sublimate it directly into a gas, bypassing the liquid state. And I'm talking like equatorial areas. This happens. I remember reading about a case of this happening, or seeing a demo of it somewhere in Kilimanjaro. I don't remember where in the internet I was when I looked at that, but so the problem with water vapor is that as humans release other greenhouse gases like carbon dioxide and chlorofluorocarbons into the atmosphere, those ones re-radiate the heat. They absorb the heat and kind of like, oh, let's warm up. And then that warms things up, that puts more energy into the system. And when there's more energy, when it's warmer, more evaporation happens. And then you have more water vapor there that's like, hey, we want to absorb some energy too. And then it gets even warmer and more evaporation happens. So this is why water vapor, this is why water vapor is a concern. I mean, it's natural, but there's more in the atmosphere than there should be. And this is part of why weather patterns can really be impacted by this. CO2 is an anthropogenic, meaning caused by humans, greenhouse gas. It has been increasing in Earth's atmosphere and it has been measured directly to be increasing since 1958. 1958, it's about 315 parts per million. Now it's probably, it looks like it's getting to be about 415, getting close, 410. So that's 100 parts per million increase at Mauna Loa Observatory in Hawaii, where I'd like to go on a field trip. So yes, there are natural sources of carbon dioxide. I'm breathing right now. I'm breathing out carbon dioxide. So is my cat. Oh, she's breathing a lot of CO2 now. Now, decomposition also releases quite a bit of CO2 in the ocean atmosphere exchange. So CO2 goes back and forth between the ocean and the atmosphere quite a bit naturally. Now, but the anthropogenic sources are cause for concern. Fossil fuel combustion, so driving my truck around, factories, and electricity, which is running this computer. Burning wood, which I'm going to do soon. When it gets cold, I like to light fires in my wood stove. And deforestation, you're removing a carbon sink, something that sequesters carbon. You're leaving slash in its wake. All of that brush, which is going to decompose, and eventually some of that will be burned or used for building materials, in which case eventually it'll decompose and be released. So methane is about 30 times more powerful than CO2 as a greenhouse gas on a 100-year scale, and 80% more powerful on a 20-year scale. So today, about 60% of methane in the atmosphere comes from anthropogenic sources. You might say, oh, well, Miss, cow's not a human, but would there be as many cows if there weren't humans? I think not. Those cows are pretty needy. I don't think many of them are going to really survive in probably the ones out west, but then eventually they would become overpopulated and the bears and wolves would eat them. So without humans. So volcanoes can release methane, those good old volcanoes. Wetlands do too. There's a lot of decomposition in wetlands, and that releases methane as well. Thawing permafrost. But the anthropogenic sources of methane include coal, rice paddies, they release a lot of methane, and cows, landfills, and leaks from oil drilling sites. Nitrous oxide N2O, different than atmospheric nitrogen, which is N2 gas, the nitrogen gas. This is 300 times more powerful than CO2 as a greenhouse gas on a 100-year scale. And this is naturally released from soils and bodies of water in the nitrogen cycle, which you can see a diagram of here. We're going to be measuring that with some of the fish tanks in school. I'm going to see if anybody has a fish tank still. I used to, and it's gone. COVID. The human sources of nitrous oxide include fertilizer and agriculture. There's tons and tons of fertilizer used in commercial agriculture. Fossil fuel combustion can also release nitrous oxide, and the wastewater treatment. Ozone is helpful or harmful depending on where it is in the atmosphere. Stratospheric ozone is good. Tropospheric ozone is bad. So ozone way up in the stratosphere, way up in the atmosphere is great and helps to block UV light. But at ground level, it's dangerous. It's a dangerous pollutant and can have harmful health impacts as well. This is a secondary pollutant because it's not emitted directly, but it's formed when nitrogen oxides and VOCs are in the presence of sunlight. They react to form ozone. So it's considered secondary because it has to undergo a chemical reaction with these other two lovelies before becoming ozone. So you can also get ozone. The good stratospheric ozone is generally created by lightning strikes. Basically, the lightning zapping the oxygen molecules together. And yeah, it's kind of fun to say ozone. CFCs, chlorofluorocarbons, are a man-made greenhouse gas. So back in the 80s, there was a lot of hairspray. Like, if you think my hair is big, it would be like, ha. Well, maybe not like that, but so until an international decision to stop using them, the Montreal Protocol happened in the 80s. People were, hair spraying it up. Aquanet, it was in refrigerators. It was in other aerosols too. And this is made in the lab, and my HVAC kids know all about this. This is a really powerful greenhouse gas. And the reason why it absorbs heat, so that's why it's something that's desirable for refrigerants, because it's able to take the heat out of the system and get it, and thereby cool things down because it's absorbing the heat. And yeah, but it's really, you don't want it in the atmosphere. It's wicked powerful. So what is the effect of the greenhouse effect? Wow, that was redundant. On the environment. So we have sea ice melting. We have the sea level rising. And that's partly because of the ice melting. It's partly because when water is warmer, it expands. There's thermal expansion of water. Ocean acidification. So coral reefs are being bleached. We have extreme weather events. Wildfires. In California, Oregon, out west, it's a mess right now. Now, one of the big problems with this, droughts, which, these kind of go together. A problem with the sea ice melting is ice is very reflective. It has a high albedo. And as it melts, you have more dark, lower albedo ocean, which can then absorb more heat, increase the temperature. Then more ice melts, and you have even more heat absorbed. So this is another positive feedback loop that just drives even more of the greenhouse effect, drives even more warming. So what is the effect on human health? Well, we've learned about the urban heat island effect and how people tend to die during heat waves, heat exhaustion. There's a lot of air pollution associated with the greenhouse effect, and that causes a lot of respiratory issues in people. There's extreme weather incidents. As extreme weather occurs, people are at risk and people can get harmed and die. Another problem is that it's changing a lot of the weather patterns, and it's in some areas of the world where you have droughts, you have a lack of food. Also, disease ranges are changing and they're spreading. We're seeing a lot different diseases, tick-borne diseases in particular, and mosquito-borne diseases here in Massachusetts than we've ever seen before because it's warmer. Some of the disease vectors, the mosquitoes and the ticks, are moving north, bringing their yucky diseases with them, like babesiosis and Lyme disease is spreading north. Lovely. So that is it for my video. I hope you enjoyed it, and I hope you have a wonderful day. Hope you learned something new. Have a good one.